This documentary was painstakingly produced over 49 days, a labor of love to bring you the most comprehensive and awe-inspiring facts about the cosmos and the universe. With a runtime of 155 minutes, it delves deep into the journey of the universe, from its birth to its potential death, alongside the many theories that attempt to explain it all. For thousands of years, humans have pondered the origin of the universe. Thanks to cutting-edge science, we are now closer than ever to understanding the greatest cosmic mystery. What triggered the Big Bang some 13.8 billion years ago? In this film, we explore groundbreaking theories and compelling evidence in an attempt to answer one of the most fundamental questions of all: what caused the Big Bang? The Big Bang theory is the most widely accepted scientific explanation for the origin of our universe. It proposes that the universe began approximately 13.8 billion years ago from an extremely hot and dense state. At that moment, all the matter, energy, and space we know today began to expand rapidly. This expansion has continued ever since, supported by multiple lines of observational evidence, including the redshift of distant galaxies. In the first few minutes after the Big Bang, the universe was a chaotic sea of intense heat and density, giving rise to subatomic particles like protons, neutrons, and electrons. As the universe expanded and cooled, these particles began to bind together, forming the simplest atomic nuclei. Around 380,000 years after the Big Bang, the universe had cooled enough for these nuclei to capture electrons and form atoms, primarily hydrogen, allowing light to travel freely for the first time. This moment gave birth to the cosmic microwave background radiation, or CMB. The CMB is a crucial piece of evidence supporting the Big Bang theory. It's the afterglow of the heat from that primordial explosion, still detectable today as a uniform microwave signal stretching across the cosmos. In addition, the abundance and distribution of hydrogen and helium in the observable universe align closely with the predictions of Big Bang nucleosynthesis models, further reinforcing the theory. We also observe that galaxies are moving away from us, and the farther they are, the faster they appear to be receding. This observation, known as Hubble's law, confirms that the universe is still expanding, a natural consequence of an origin point like the Big Bang. Rewinding this expansion mathematically leads us back to a singular event, not only marking the beginning of space and time, but also the birth of all matter and energy in our universe. The Big Bang theory was originally proposed in the early 20th century by Belgian priest and astronomer Georges Lemaitre. In 1927, he suggested that the universe was expanding from a primeval atom, an initial point that marked the beginning of everything. His groundbreaking idea was based on his understanding of Einstein's general theory of relativity and his observations of redshifted light from distant galaxies. Though Lemaitre laid the theoretical groundwork, it wasn't until the 1930s, with the observations of Edwin Hubble, that the theory gained broader acceptance. Hubble discovered that galaxies were moving away from each other, and that there was a direct relationship between their distance and their speed of recession. This provided key evidence for Lemaitre's theory, transforming it into the Big Bang model we know today. Ironically, the term Big Bang was coined by British scientist Fred Hoyle during a BBC radio broadcast in 1949, not to promote it, but to mock it. Hoyle was a proponent of a rival theory known as the steady-state theory, which held that the universe was eternal and unchanging on large scales. Yet, by using the phrase Big Bang, Hoyle unintentionally gave a memorable name to the theory that would go on to become the dominant explanation of our cosmic origins. Ironically, although the term Big Bang was coined as a label of opposition, it ultimately became the widely recognized name for the theory. Over time, advancements in technology and observational science, such as the discovery of the cosmic microwave background radiation, CMB, and the measured abundance of hydrogen, have solidified the Big Bang theory as the leading explanation for the origin of the universe. This journey across disciplines demonstrates how scientific understanding evolves through the combined contributions of many individuals. Among the extensive body of evidence supporting the Big Bang, 3 pillars stand out most prominently. First and foremost is the cosmic microwave background radiation, a faint glow that fills the universe, representing the afterglow of the early universe's heat. The CMB gives us a snapshot of the universe approximately 380,000 years after the Big Bang, when atoms first formed and light was finally able to travel freely. Its near-perfect uniformity in distribution and temperature matches the theoretical predictions of a hot, dense origin, providing one of the most compelling confirmations of the Big Bang model. The second key piece of evidence is the observed abundance of light elements, such as hydrogen, helium, and lithium. The Big Bang nucleosynthesis model predicts that these elements would have formed in precise proportions within the first few minutes of the universe's existence. Measurements of these elements across the cosmos match those predictions very closely, reinforcing our understanding of the universe's early conditions and validating the model's credibility. Third is the redshift of distant galaxies, a phenomenon first documented by Edwin Hubble. Galaxies appear to be moving away from us, and the farther they are, the faster they seem to recede. This observation confirms that the universe is expanding, a cornerstone of the Big Bang scenario. It supports the idea that the cosmos once existed in a much more compact, hot, and dense state from which it has been expanding ever since. Finally, the large-scale structure of the universe, including galaxy clusters and the cosmic web, can be explained by simulations based on Big Bang cosmology. These simulations suggest that today's vast structures evolved from tiny density fluctuations in the early universe, ultimately leading to the massive galaxies and formations we observe today. Taken together, this body of evidence forms a robust framework supporting the Big Bang theory as the most coherent explanation for the origin and evolution of the cosmos. According to the theory, the universe is approximately 13.8 billion years old. This estimate comes from a combination of methods, including measurements of the CMB, the motions of galaxies, and our understanding of stellar evolution. Each of these offers critical insights into the events that have unfolded since the universe's inception. The 13.8 billion year estimate is primarily based on detailed measurements of the CMB, particularly data collected by missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite. By analyzing tiny fluctuations in temperature across the sky, scientists can infer the conditions under which the universe became transparent to radiation, around 380,000 years after the Big Bang, and work backward to estimate the age of the universe. This estimate is also reinforced by the study of distant galaxies and their redshifts. Since some galaxies are observed to be moving away from us at significant speeds, their distances can be used to calculate how long the universe has been expanding. The Hubble constant, which defines the rate of this expansion, plays a key role in these calculations, helping astronomers determine that the universe is indeed about 13.8 billion years old. This timeline marks a remarkable journey, from the fiery beginnings of the cosmos to the vast structured universe we see today. In its earliest moment, the universe existed in an incredibly hot and densely packed state, a singularity in which all matter, energy, space, and even time itself were compressed into a single, infinitesimal point. Temperatures soared to unimaginable levels, trillions of degrees, creating an environment far too hostile for ordinary matter to exist. Particles collided with enormous energies, forming a chaotic soup of fundamental particles such as quarks and electrons. This initial phase is known as the Planck epoch, and it lasted for only a tiny fraction of a second, about 10 man-per-second after the Big Bang. During this period, the laws of physics as we currently understand them began to emerge. Shortly afterward, the universe underwent a dramatic and rapid expansion known as cosmic inflation. This process smoothed out irregularities and allowed the universe to cool rapidly, paving the way for simpler particles to form. As expansion continued, quarks bound together into protons and neutrons, setting the stage for the creation of atomic nuclei. This brief period, known as the era of nucleosynthesis, occurred within the universe's first few minutes and produced most of the hydrogen in the universe today, along with traces of helium and lithium. During this time, the universe was still opaque. Photons couldn't freely move through the dense plasma of particles. It wasn't until about 380,000 years after the Big Bang that the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. This transition marked the end of the recombination era and allowed light to travel freely for the first time, leading to the release of the cosmic microwave background radiation, CMB, a critical milestone in the universe's evolution. From this initial chaos, the universe began its journey toward the structured cosmos we observe today. The cosmic microwave background radiation is one of the most powerful pieces of evidence supporting the Big Bang theory. This faint glow, which fills all of space, is the thermal remnant from the moment the universe became transparent. At that time, the universe was still a hot, dense plasma, and light could not escape. But as the universe expanded and cooled, it reached a point, about 380,000 years post-Big Bang, when atoms formed, and photons were finally free to travel. The radiation released during that epoch initially existed as high-energy electromagnetic waves, but over billions of years of cosmic expansion, those waves were stretched and cooled, shifting into the microwave range of the spectrum. Today, we detect this radiation as an almost perfectly uniform glow with a temperature of about 2.7 Kelvin, just above absolute zero. This uniformity across the sky offers strong support for the idea that the universe originated from a hot, dense state. Moreover, the tiny fluctuations in the CMB's temperature match the predictions of the Big Bang theory almost exactly. These small variations reflect minute density differences in the early universe, which ultimately gave rise to the large-scale structures we see today: galaxies, galaxy clusters, and cosmic filaments. By studying the patterns in these temperature fluctuations, scientists can extract vital information about the rate of expansion, the composition of the universe, and its overall geometry. The CMB has thus become an essential tool for cosmologists to test and refine models of the universe's evolution. Observations by missions such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite have provided extremely precise measurements of the CMB. The data collected have confirmed key predictions of the Big Bang theory about the age of the universe, its rate of expansion, and the relative abundance of light elements created during nucleosynthesis. The cosmic microwave background radiation, CMB, stands as one of the most striking pieces of evidence supporting the foundational principles of the Big Bang theory and our understanding of cosmic origins. One key development in modern cosmology is the theory of cosmic inflation, which proposes that the universe underwent a phase of rapid exponential expansion immediately following the Big Bang. This expansion occurred during a tiny fraction of a second, known as the Planck epoch, during which the universe expanded from subatomic scales to nearly galactic scales in less than 100,000th of a second. This extraordinary burst of inflation helps address several key observations that the original Big Bang theory alone could not fully explain. One of inflation's most profound implications is its ability to account for the remarkable uniformity of the cosmic microwave background radiation. Without inflation, regions of the universe currently separated by vast distances would not have been in causal contact, making it difficult to explain why the temperature and features of the CMB are so consistent across the sky. Inflation suggests that these distant regions were once extremely close together, allowing them to reach thermal equilibrium before expanding far apart. Another significant outcome of inflation is that it offers a mechanism for the large-scale structure of the universe. During inflation, tiny quantum fluctuations were stretched to cosmic scales, seeding the density variations that would eventually evolve into galaxies and clusters of galaxies. This process provides a natural explanation for the irregularities we observe in an otherwise uniform universe. Inflation also predicts that the universe should be geometrically flat, with its shape determined by the total density of matter and energy. Observations, particularly those of the CMB, support this prediction, indicating a flat universe consistent with inflationary models. Moreover, inflationary theory offers a compelling framework to explain the recently observed acceleration in the expansion of the universe. It suggests that the scalar field that once drove inflation may still influence cosmic expansion, possibly linked to what we now call dark energy. In summary, the theory of inflation greatly enhances the explanatory power of the Big Bang model. It provides elegant solutions to the CMB's uniformity, the origin of large-scale structures, and the geometry of the universe. Another crucial line of evidence for the Big Bang comes from the observed abundance of light elements, particularly hydrogen, helium, and lithium. These elements were formed through a process known as Big Bang nucleosynthesis, which occurred during the first few minutes of the universe when extreme temperatures and pressures enabled nuclear reactions. As the universe expanded and cooled, protons and neutrons were able to fuse, forming atomic nuclei. According to the Big Bang nucleosynthesis model, roughly 75% of the universe's normal matter should be hydrogen, about 25% helium, and trace amounts of lithium and beryllium. Observations of the primordial abundances of these elements closely match theoretical predictions. For example, the ratio of helium to hydrogen in the universe is almost exactly what Big Bang theory predicts. This strengthens the argument that these elements were produced during an early nucleosynthesis phase, under conditions expected shortly after the Big Bang. Measurements of light element abundances provide critical insights into the conditions of the early universe. When astronomers study the composition of ancient stars and interstellar gas clouds, they consistently find relative ratios that agree with the predictions of the Big Bang model. The uniform distribution of hydrogen across the universe further indicates a common origin, supporting the view that these elements were forged during a universal event in the early stages of cosmic history. The presence and distribution of light elements such as hydrogen and helium offer another crucial layer of evidence supporting the Big Bang theory. Their relative abundances help refine our understanding of the universe's expansion rate and matter density. Discrepancies between observational data and theoretical predictions challenge our models, prompting further research and continuous refinement of cosmological theories. Overall, the observed abundance of hydrogen strongly supports the Big Bang model, revealing a clear connection between the conditions of the early universe and the chemical landscape we observe today. When scientists refer to T=0 in the context of the Big Bang, they are describing the precise moment when time itself began, as we currently understand it. This marks the origin of the universe, a point where all matter, energy, space, and time were concentrated in an extremely hot and dense singularity. The label T=0 serves as a boundary beyond which our current understanding of physics breaks down. In such extreme conditions, the known laws of physics cease to be reliable. At this point, the universe is thought to have contained all fundamental forces, gravity, electromagnetism, and the nuclear forces, in a single, unified state. As the universe began to expand and cool from this singularity, these forces separated into the distinct interactions we observe today. This transformation marks the beginning of cosmic evolution, eventually leading to the formation of galaxies, stars, and planetary systems. It's important to emphasize that discussions surrounding T=0 highlight the limits of our scientific understanding, rather than pinpointing a moment we can experimentally verify. The concept challenges intuition because we cannot meaningfully speak of before the Big Bang. Time itself began at that moment. Thus, there is no before in the traditional sense. The transition from T=0 set the stage for key events such as cosmic inflation, nucleosynthesis, and the formation of atomic nuclei in galaxies. This phrase, T=0, also reflects the profound complexity of cosmology, as scientists attempt to reconstruct the universe's history from this mysterious starting point. Although many questions remain about the very beginning, T=0 remains central to understanding the evolution of the cosmos as we know it. The question of what existed before the Big Bang is both profound and immensely challenging. It confronts the limitations of current scientific frameworks and forces us to question the nature of time and space themselves. According to the standard Big Bang model, the universe began approximately 13.8 billion years ago from a singularity, an extremely hot, dense point where space-time itself came into being. This means that any attempt to discuss before the Big Bang enters a domain where the very concept of time may be meaningless, since all known dimensions, including time, emerged from that singular event. From the perspective of modern physics, time is not a static backdrop, but an integral part of space-time. Thus, asking what came before time may simply be a poorly formed question, because it assumes a temporal framework that did not exist. However, speculative theories have been proposed that go beyond the conventional Big Bang framework. For example, some models suggest the universe may undergo cyclic periods of expansion and contraction, hinting that our universe could be just one phase in an eternal cosmic cycle. It is possible that our universe is just one among many, perhaps following a previous cosmic phase. Advanced frameworks like string theory have also proposed the possibility of a multiverse or alternative dimensions, domains where different physical laws might apply. However, these ideas remain largely theoretical and have not gained broad acceptance in the scientific community. While they offer fascinating speculation, current observational limitations mean we cannot definitively determine whether anything existed before the Big Bang. Exploring such concepts has sparked ongoing inquiry and debate, pushing the boundaries of our understanding of time, space, and the fundamental nature of the cosmos. As it stands, the notion of conditions before the Big Bang remains an unresolved mystery, one that hints at deeper questions yet to be answered in cosmology. Eternal inflation is a theory that extends the idea of cosmic inflation by proposing that inflation may not have been a one-time event in the early universe, but rather an ongoing process occurring in different regions of space-time. According to this concept, although our observable universe underwent a brief period of rapid expansion shortly after the Big Bang, inflation might still be continuing indefinitely in other parts of the universe. This leads to the formation of a potentially infinite number of bubble universes, each emerging from this eternal process. In the eternal inflation model, the expansion is driven by a scalar field, often referred to as the inflaton field. This field can exist in different energy states. Certain regions settle into low-energy configurations and stop inflating, forming pocket universes like ours, while other regions remain in a hot, dense state and continue expanding. As a result, inflation never completely ends, and new universes can continuously emerge, forming a vast multiverse where each universe might have different physical laws and properties. One intriguing implication of eternal inflation is that it may help explain why our universe exhibits such remarkable isotropy and homogeneity. The stretching of quantum fluctuations to cosmic scales during inflation helped seed the initial conditions for structure formation. However, within the eternal inflation framework, these fluctuations occur endlessly, generating a landscape of diverse universes with varying characteristics. While the idea of eternal inflation opens the door to exciting possibilities, it also poses challenges for scientific verification. If our universe is merely one of countless others, directly observing or testing the existence of others becomes exceedingly difficult. For this reason, eternal inflation remains a theoretical construct that provides valuable insights into the broader nature of reality and the possible conditions beyond our own universe. Ongoing advancements in cosmological observations and theoretical research will be essential to exploring the implications of eternal inflation and understanding its potential role in shaping our view of the universe's origin. The cyclic universe model presents an alternative vision for cosmic evolution, one where the universe doesn't begin from a singular point, but instead goes through endless cycles of birth, expansion, contraction, and rebirth. Each cycle begins with an event similar to the Big Bang, followed by a period of expansion, then gradual slowing, and ultimately a collapse known as the Big Crunch. This collapse could lead to conditions that resemble the original starting point, potentially restarting the entire cycle once again. The cyclic model offers one of the most compelling challenges to the traditional Big Bang paradigm. Its significance lies in the profound implications for our understanding of time and the nature of the universe itself. While the Big Bang theory suggests a single point of origin, the cyclic model implies that the universe is eternal, with no beginning or end. This perspective raises fundamental questions about the creation of matter, energy, and the laws of physics, suggesting that our current state of the universe is merely one phase in an ongoing cycle, not a unique event. Moreover, the cyclic universe introduces the idea that conditions may vary with each iteration. In later cycles, for instance, the values of physical constants or fundamental forces could differ, potentially giving rise to entirely different universes in each cycle. These variations might also help explain certain observed phenomena in our own universe, such as the uniformity and isotropy seen in the cosmic microwave background, which may be influenced by rules governing transitions between cycles. While the cyclic model is compelling and offers potential solutions to some conceptual challenges posed by the Big Bang, it remains highly speculative. There are significant scientific obstacles in demonstrating the mechanism by which expansion transitions into contraction, and in understanding how a big crunch could lead to a new Big Bang without violating physical laws. As such, although the cyclic universe presents an intriguing line of inquiry, it continues to be a subject of active debate among cosmologists and physicists exploring the complex story of the universe's past, present, and future. The Big Bounce theory is another cosmological model that proposes the universe undergoes a series of expansions and contractions, rather than originating from a singular event known as the Big Bang. According to this idea, the universe does not begin at a single point, but instead rebounds from a previous contraction phase into a new phase of expansion. This suggests the universe may be cyclical, repeating these bounces indefinitely without a definitive beginning. Rooted in classical general relativity and informed by quantum gravity effects, the Big Bounce allows scientists to explore the conditions that arise during the extremely dense phases of a collapsing universe. Within this framework, it is theorized that instead of reaching a state of infinite density and an origin point, the universe undergoes a quantum transition, where the laws of physics once again shift, allowing the universe to bounce back into a new expansion phase, similar in behavior to what is described by the Big Bang theory. One of the major advantages of the Big Bounce is that it avoids the singularity problem associated with the traditional Big Bang model, which prompts difficult questions about what could have existed before the beginning. The Big Bounce, instead, implies that there was no singular origin, enabling cosmologists to explore a universe that evolves continuously without requiring an initial state to be defined. Despite its appeal, the theory faces several challenges, particularly regarding the exact mechanism of transition from contraction to expansion and the governing physics behind that process. Further theoretical work and empirical validation are needed to strengthen the model. While some versions of the Big Bounce do produce observable predictions that can be compared with current measurements of the universe, establishing such connections remains a complex and ongoing task. In summary, the Big Bounce opens new possibilities for understanding the universe's past and future, offering an alternative framework for cosmic evolution. One that reframes the origin not as a beginning, but as part of an eternal rhythmic process. In contrast to the traditional Big Bang theory, string theory offers a captivating alternative perspective on the origin of the universe. As research continues, scientists are exploring the implications of this model and seeking evidence that could either support or challenge its claims. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but instead tiny vibrating strings. These strings can be either closed loops or open lines, and their various vibrational modes correspond to different particles, such as quarks and electrons. By constructing the universe in this way, string theory provides a framework that attempts to unify quantum mechanics with general relativity, potentially offering answers to some of the most fundamental questions about the origins of the cosmos. One of the significant implications of string theory is the introduction of extra dimensions beyond the familiar 3 spatial dimensions and 1 temporal dimension. While our everyday experiences are confined to 4 dimensions, string theory suggests the existence of additional dimensions that could help unify the fundamental forces of nature. These extra dimensions may also play a role in the creation of the universe, as the conditions within them could influence the properties of strings and fundamental forces. Furthermore, string theory offers a potential mechanism for the dynamics of the early universe through a concept known as the string landscape. This landscape refers to the vast diversity of possible physical scenarios arising from different configurations of these extra dimensions. Within this context, the universe we observe may have emerged from a specific configuration of dimensions and strings, resulting in a unique set of physical laws. This landscape opens up a broader pathway that not only includes the creation of our universe, but also the potential for other universes with different characteristics within a multiverse. Additionally, some models of string theory incorporate the concept of high-dimensional objects called branes, upon which strings can reside. Interactions between branes may create conditions similar to those of the Big Bang, where collisions or mergers of branes could trigger rapid expansions of the universe. Such events could resemble cosmic inflation and potentially lead to configurations similar to our current universe. Although string theory presents a compelling framework with profound implications for understanding the origin of the universe, it remains largely theoretical and faces significant challenges, particularly due to the extremely small scale of strings, which lies beyond current technological capabilities. As a result, many of its predictions lack direct experimental verification. Nevertheless, as research progresses, scientists are striving to explore the predictions of string theory, seeking empirical evidence that could support its claims and provide a deeper understanding of the universe's origins. The concept of a multiverse suggests that our universe may be just one among countless others, each potentially possessing different properties, physical laws, and even differing aspects of reality itself. This idea expands our understanding of the cosmos far beyond the single universe framework that many are familiar with. Different theories propose various types of multiverses, some stemming from quantum mechanics, while others are tied to cosmic inflation. The rapid expansion following the Big Bang, which occurred approximately 13.8 billion years ago, marked the origin of the universe as we know it. This moment created space, time, matter, and energy in an instant. The relationship between the Big Bang and the multiverse concept arises mainly from certain cosmological models, especially those suggesting that our universe is just one region within a much larger and more diverse cosmic structure. Our universe may be just one bubble among many in a much larger cosmic foam. As expansion began, certain regions of space inflated faster than others, creating isolated bubble-like universes that are causally disconnected from each other. These alternate universes could operate under different physical laws, leading to profound differences, such as variations in the constants of nature or even entirely different dimensional frameworks. The implications of this are enormous, prompting reflections on the possibility of radically different forms of life and suggesting a reality far beyond what we can currently observe. While evidence for a multiverse remains elusive, ongoing research in cosmology and physics continues to expand our understanding, fueling excitement and speculation within the scientific community. Quantum fluctuations, predicted by quantum mechanics, refer to temporary changes in energy at specific points in space. These arise due to the inherent uncertainty in energy levels at the quantum scale. For example, Heisenberg's uncertainty principle states that the more precisely we know a system's energy, the less precisely we can know its position, and vice versa. This interplay creates an environment in which energy can spontaneously appear and disappear, giving rise to phenomena that may seem extraordinary from a classical point of view. These fluctuations play a critical role in a variety of phenomena, especially in the early universe shortly after the Big Bang, when the cosmos was in an extremely hot and dense state. During this chaotic phase, quantum fluctuations caused tiny variations in energy density throughout the universe. Over time, these minute differences had profound effects on the energy distribution, initiating the clumping of matter that would eventually form galaxies, stars, and planets. The influence of quantum fluctuations extends beyond the early universe. They are also tied to the concept of vacuum energy, which describes the lowest possible energy state of a quantum field. As a result, even empty space contains virtual particles, constantly appearing and disappearing, driven by these fluctuations. This challenges the classical notion of a vacuum and reveals it as a dynamic arena of continuous activity. Exploring quantum fluctuations opens up fascinating discussions about the nature of reality. They emphasize that the universe is shaped not only by large-scale forces we observe, but also by the chaotic and unpredictable behavior at atomic and subatomic levels. the ripple effects of these fluctuations continue to influence our understanding of the cosmos. Quantum fluctuations are believed to have had a significant impact on the fabric of the universe both before and after the Big Bang. In the early universe, governed by quantum mechanics, these fluctuations introduced variations in energy density on small scales. This randomness played a crucial role in shaping the overall structure and evolution of the cosmos. During this extreme phase of energy and density, quantum fluctuations may have created high-density regions surrounded by lower-density zones. These variations set the stage for cosmic inflation, which occurred almost instantly afterward. The inflation model suggests that this exponential growth smoothed out the microscopic variations while stretching them across vast distances. Tiny fluctuations became the seeds of the large-scale structures we observe today, such as galaxies and galaxy clusters. Moreover, as inflation ended, these quantum fluctuations became imprinted onto the fabric of space-time. As the universe cooled, the energy density collapsed into matter, and the regions with slight density increases began to gravitationally attract more matter. Over billions of years, these small perturbations eventually led to the formation of stars. The gravitational clustering of galaxies and other cosmic structures stems from quantum fluctuations, highlighting the interplay between quantum phenomena and cosmic scales. This connection invites us to consider how unpredictable particle behavior on the smallest scales can lead to the grand and orderly universe we observe today. Understanding this relationship not only deepens our grasp of the universe's origin, but also resonates with the profound nature of reality, where chaos and order are intricately intertwined. Vacuum energy is a fascinating concept that describes the presence of energy in empty space, or what we commonly refer to as a vacuum. Contrary to the intuitive idea that a vacuum is completely empty, quantum mechanics reveals that even the emptiest space at the quantum level is teeming with activity. Virtual particles constantly appear and disappear due to fluctuations in the vacuum state's energy. These transient particles contribute to an overall energy associated with the vacuum itself. The concept of vacuum energy arises from the principles of quantum field theory, which asserts that every point in space is influenced by fields associated with different particles. When measuring the vacuum's energy, it becomes clear that these fluctuations do not simply cancel each other out. Instead, they create a mechanical energy level. This energy may have significant implications for cosmic phenomena. For instance, vacuum energy plays a role in the concept of dark energy, which is thought to drive the accelerating expansion of the universe. As researchers examine vacuum energy, they find it challenges conventional notions of reality. If a vacuum is not truly empty, it raises profound questions about the nature of existence itself. It suggests that space possesses properties that can influence the dynamics of the cosmos. This realization has led scientists to explore how fundamental forces and particles interact on scales that are difficult to observe, potentially shaping the universe in subtle but crucial ways. The potential impact of vacuum energy extends beyond theoretical physics. It sparks discussions about the ultimate fate of the universe and opens new avenues of inquiry in cosmology and particle physics. Ultimately, this captivating aspect of quantum mechanics invites us to reconsider our understanding of reality and the complex forces that govern the cosmos. The concept of vacuum energy is closely tied to theories of the universe's origin, particularly in exploring how the cosmos might have emerged from what appears to be nothing. In the moments and months following the Big Bang, the universe was a seething mass of energy, heavily influenced by quantum mechanics, including vacuum energy, which played a fundamental role in the rapid expansion that occurred during the early stages. One of the most intriguing ideas is that vacuum energy may have fueled the inflationary phase of the universe. According to the inflation model, a brief period of exponential expansion occurred after the Big Bang. Fluctuations in vacuum energy may have created regions with varying densities, leading to an uneven distribution of matter as the universe expanded. These fluctuations became the seeds of the large-scale structures we see today, such as galaxies and galaxy clusters. Furthermore, as inflation ended, the energy associated with these fluctuations may have contributed to the growth of matter, further shaping the structure of the universe. The link between vacuum energy and the origin of the universe illustrates the delicate balance between chaos and order, a balance that governs cosmic evolution. The zero-point energy field refers to the lowest possible energy state of a quantum system. Even at absolute zero temperature, this field retains residual energy. This concept, derived from quantum mechanics, reveals that particles persist in motion and fluctuation due to the inherent uncertainty in both energy and position. Particles are never completely at rest. This means that even in a perfect vacuum where no particles are present, energy fluctuations still result in a non-zero mechanical energy, known as zero-point energy. On the microscopic level, fields such as electromagnetic fields and electron fields exhibit this form of energy. These fields remain in a constant state of excitation. Moreover, the interaction between virtual particles and vacuum energy raises important questions about the nature of reality. It challenges our understanding of what constitutes a vacuum and invites us to reconsider the fundamental nature of space itself. The concept of virtual particles not only enhances our understanding of the early universe, but also bridges the gap between quantum mechanics and cosmology. It provides insights into how microscopic phenomena can lead to the vast cosmic structures we see today. The four fundamental forces of nature govern the interactions and behavior of matter and energy throughout the entire universe. These are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each of these forces plays a distinct role in shaping the cosmos, from the tiniest atomic particles to the most magnificent astronomical structures. Gravity is perhaps the most familiar of the fundamental forces. It governs the attraction between masses, keeping us anchored to Earth and controlling the motion of celestial bodies. Despite being the weakest of the four forces in terms of strength, its long-range nature gives it a profound influence across vast distances, pulling galaxies together and shaping the structure of the universe itself. The electromagnetic force is responsible for the interaction between charged particles. It governs phenomena we encounter in everyday life, including chemical reactions, atomic behavior, and the propagation of light. Electricity arises from stationary charges, while magnetism is associated with moving charges. Electromagnetism is far stronger than gravity and has a similar range, but it is highly dependent on the charge of the particles involved. The weak nuclear force operates at the subatomic level and is crucial to processes such as beta decay, in which a neutron in an atom can transform into a proton, releasing an electron and a neutrino. Though its range is limited to atomic distances, the weak force plays an essential role in powering stars and facilitating nuclear fusion. On the other hand, the strong nuclear force binds protons and neutrons together within atomic nuclei. It is extremely powerful but operates over a very short range, effective only at distances comparable to the size of an atomic nucleus. This force is responsible for maintaining the stability of matter by overcoming the electromagnetic repulsion between positively charged protons, where virtual particles momentarily appear and vanish due to energy fluctuations. This phenomenon does not imply that these fields contain observable, tangible particles. Rather, it indicates that they represent a dynamic and perpetually active state, where energy exists even in the absence of matter. Zero-point energy plays a significant role in various physical theories, including quantum field theory and cosmology. In the context of vacuum energy, it helps explain phenomena such as dark energy, which is responsible for the accelerated expansion of the universe. The zero-point energy field as a background influences the behavior of particles and affects the large-scale structure of the cosmos. Understanding zero-point energy also raises intriguing questions about the possibility of harnessing this energy. Although zero-point energy permeates the universe, the idea of extracting it for practical use remains speculative and highly challenging. Nevertheless, this area of inquiry continues to captivate scientists and researchers as they seek to uncover deeper insights into its implications for fundamental physics, energy generation, and technological innovation. Virtual particles are a fundamental concept in quantum mechanics, and their existence is crucial to our understanding of the early universe. These particles emerge due to energy fluctuations in the vacuum. In the context of the early universe, virtual particles flourished under the extremely hot and dense conditions shortly after the Big Bang. During this turbulent time, these particles may have created transient energy fluctuations across the entire fabric of space-time. This dynamic activity suggests that the universe was never a calm, empty void, but rather a seething environment full of energetic processes that ultimately contributed to cosmic evolution. Virtual particles become particularly relevant when considering cosmic inflation, a theory proposing that the universe underwent rapid expansion immediately after the Big Bang. During inflation, quantum fluctuations may have created variations in energy density, producing slightly different regions of space. These fluctuations, associated with virtual particles, became the seeds for the structures we observe today, such as galaxies and galaxy clusters. When inflation ended, the energy tied to these fluctuations may have contributed to the growth of matter, further shaping the structure of the universe. These four fundamental forces interact in complex ways, influencing everything from the behavior of subatomic particles to the evolution of the cosmos. They are essential because they form the foundation for how we perceive and understand the universe. In the earliest moments after the Big Bang, the universe existed in an extremely hot and dense state. Under these extreme conditions, it is theorized that the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were once unified into a single force. This idea arises from the notion that at extremely high energy levels, such as those present immediately after the Big Bang, the distinctions between forces become negligible, allowing them to interact seamlessly. Physicists refer to this phase as the Grand Unification Epoch, which occurred approximately 10^-8 after the Big Bang. At that time, the conditions were so extreme that the energy levels allowed the fundamental forces to merge into one unified interaction. Specifically, grand unified theories, GUTS, in particle physics suggest that the strong nuclear force, the weak nuclear force, and electromagnetism merged into a single force, while gravity remained separate due to its distinct characteristics. As the universe expanded and cooled, conditions gradually changed, leading to the separation of this unified force into the distinct forces we observe today. First, the grand unified force split into the strong nuclear force and the electro-weak force, the latter being a combination of electromagnetism and the weak nuclear force. With further cooling, the electro-weak force itself split into separate electromagnetic and weak forces. Gravity continued to operate independently throughout. This sequence of unification and subsequent separation not only marks a significant transformation in the early universe, but also laid the groundwork for the development of matter as we know it. The electroweak force, one of nature's fundamental interactions, unified two of the known four forces, electromagnetism and the weak nuclear force. This unification is described by electroweak theory, which was developed in the mid-20th century by physicists including Sheldon Glashow, Abdus Salam, and Steven Weinberg. Their work demonstrated that at high energy levels, the electromagnetic force, which governs interactions between charged particles, and the weak nuclear force, which governs processes such as nuclear decay, are manifestations of a single underlying force. The separation of the electroweak force from the strong nuclear force occurred during a phase in the early evolution of the universe known as the electroweak epoch. This transition is believed to have taken place approximately 10^-seconds after the Big Bang, when the universe had cooled enough for these forces to begin operating independently. Prior to this separation, the three forces, strong nuclear, weak nuclear, and electromagnetic, were unified at extremely high temperatures. As the universe expanded and cooled, energy levels dropped to a point where electroweak symmetry broke. At that moment, the electroweak force split into its two constituent parts: the weak nuclear force, which operates at subatomic distances and is crucial in processes like radioactive decay, and the electromagnetic force, which governs interactions between charged particles over larger distances. This division marked a significant transformation in the early universe and paved the way for the formation of matter structure. Electroweak theory plays a critical role in the standard model of particle physics. It provides a framework that explains how particles interact through these forces and describes their properties. Understanding the electroweak force and its separation helps researchers reconstruct the conditions of the early universe and offers insights into how nature operates on the smallest scales. Gravity is believed to have separated from the other fundamental forces during the very earliest moments of the universe, possibly before the Grand Unification epoch, when the strong, weak, and electromagnetic forces were still unified. While the exact time frame for gravity's separation is not precisely defined, models suggest that it occurred within the first 10 man-square seconds after the Big Bang. In this incredibly high-energy state, distinctions between fundamental forces were negligible due to extreme conditions. However, as the universe expanded and cooled, gravity emerged as a separate force, while the other three forces remained unified for a time. Scientists speculate that gravity is fundamentally different from the other forces because of its geometric nature. It is described by Einstein's general theory of relativity, which interprets gravity not as a force like electromagnetism or the nuclear forces, but as the curvature of space-time caused by mass and energy. Gravity's early separation, preceding even the split of the electroweak force, established it as a distinct fundamental principle with a unique role in shaping the dynamics of the cosmos, governing the formation of structures such as galaxies, stars, and planets. Understanding gravity, verifying how it separated from the other forces, remains a complex and active area of theoretical physics and cosmology. Investigating the origin of gravity and its relationship to the other forces may lead to future discoveries about the fundamental nature of the universe. This includes the potential unification of gravity with the other forces through the pursuit of a theory of quantum gravity. The strong nuclear force, often simply called the strong force, is one of the four fundamental forces of nature. It is responsible for binding protons and neutrons together within atomic nuclei. It is the strongest of the four forces, yet it operates only over extremely short distances, typically less than 1 femtometer, which is about 100,000 times smaller than the diameter of a typical atom. This force is essential to the stability of matter, as it overcomes the electromagnetic repulsion between positively charged protons in the nucleus. The strong nuclear force arises from a fundamental interaction mediated by particles called gluons. These gluons act as the exchange particles, or force carriers, of the strong interaction. Gluons are massless and facilitate interactions between quarks, the building blocks of protons and neutrons. Quarks are the building blocks of protons and neutrons. They are bound together by the exchange of gluons, which generate the binding energy that unifies them. This binding energy is incredibly strong and accounts for the majority of an atomic nucleus's mass. The strong nuclear force is thought to have developed during a particular phase of the early universe, especially during the Grand Unification epoch. As the universe cooled after the Big Bang, the fundamental forces began to differentiate from their previously unified state. The strong nuclear force separated from the electroweak force when the universe reached the appropriate energy level and underwent a series of symmetry-breaking transitions. During the infant stages of the universe, quarks and gluons existed in a hot, dense environment known as the quark-gluon plasma. As the universe expanded and cooled, quarks began to combine to form protons and neutrons. This transformation occurred in a process called hadronization. The emergence of hadrons marked a crucial moment in cosmic evolution. With protons and neutrons in place, the strong nuclear force took over, allowing these particles to bind together and ultimately form atomic nuclei. In the following stage, known as primordial nucleosynthesis, further cooling of the universe, around 380,000 years after the Big Bang, allowed electrons to combine with these nuclei to form neutral atoms. This signified the end of the recombination era and led to the creation of the cosmic microwave background radiation, a relic of the early universe that we can still detect today. Quarks played a fundamental role in the early development of the universe. Transitioning from their free state in the quark-gluon plasma to becoming components of protons and neutrons, they were essential in forming atomic nuclei. These nuclei ultimately gave rise to the atoms required to build stars, galaxies, and eventually life itself. Understanding the role of quarks in the early universe offers valuable insight into the processes that shape the cosmos and the intricate relationships between fundamental particles and forces. Shortly after the Big Bang, the universe was in an unimaginably hot and dense state, teeming with elementary particles such as quarks and electrons. As the universe expanded, it cooled, allowing quarks to combine into protons and neutrons. About 3 minutes after the Big Bang, these protons and neutrons fused to form the first hydrogen nuclei, most notably single-proton hydrogen atoms, and helium nuclei consisting of 2 protons and 2 neutrons. These nuclear reactions, driven primarily by the strong force, occurred under conditions vastly different from those we observe today. The process produced roughly 75% hydrogen and 25% helium by mass, along with trace amounts of lithium and beryllium. Approximately 370,000 years after the Big Bang, the universe cooled enough for electrons to combine with these nuclei, forming neutral atoms. This period, known as the recombination era, marked the transition from a hot, ionized plasma to the formation of the first atomic gases. With radiation decoupling from matter, the universe became transparent for the first time, allowing light to travel freely and creating what we now detect as the cosmic microwave background radiation. These first atoms were essential for the evolution of the universe. They served as the foundational elements for the formation of stars and galaxies over the course of billions of years.